Good morning. Welcome to Krishna's classroom. Let us continue from where we left last time. We were working on an equivalent form of absolute continuity in a more in a different form in which we could possibly exploit while proving the fundamental theorem of calculus in the new context, of course. So let us briefly recall the statement of the theorem. I'm just repeating it. So we assume F is CAD, that is the P assumption on a closed bounded interval A. Then F is absolutely continuous on AD if and only if the divided difference functions diff is uniformly integrable So this is the statement of the theorem. We are starting with a continuous function and on a compact interval. Now we have then f an absolutely continuous function on the compact interval if and only if the divided difference functions, that is if h, f where h is the parameter running from 0 to 1 is uniformly integrable on AB. Okay, what we have assumed, what we have proved is this. We have already proved the backward implication. That means assuming the divided difference functions are uniformly integrable on AB, we concluded that f is an absolutely continuous function on the interval A. So what remains to be proved, this part is this. So we shall now take up the forward implication. That is, we assume f belongs to is absolutely continuous over the interval A. So that's what we assume. Then what we claim is the divided difference functions is uniformly integral. Now we shall outline the proof, or rather go through the various steps of the proof in detail. Now first, if absolutely continuous on AB implies F is the difference of two increasing absolutely continuous functions on. Therefore, whatever we want to prove, it is sufficient to prove for absolutely continuous functions which are increasing. Okay. Therefore, it is sufficient to prove the result for increasing absolutely continuous See, the way in which we proved this result is that we proved every absolutely continuous function is a function of bounded variation. Then we had the result that every function of bounded variation is the difference of two increasing functions of bounded variation. Okay? And these increasing functions of bounded variation, when f itself is absolutely continuous, turns out to be absolutely continuous. So that gives this result. And consequently, it is sufficient to prove this with the assumption that f is increasing and absolutely continuous. Hence, we assume without loss of generality that f is absolutely continuous and increasing. So that's the solution. So we have reduced the problem to proving it for absolutely continuous functions which are increasing. Now, the assumption that f is increasing implies the divided difference function is then or equal to 1 or r non-negative. This is immediate from the condition of that the functions are increasing. Okay. Now we want to conclude that this collection of functions are uniformly integrable. Okay, so let us see how we proceed. Okay. So let us do this part, and okay. Uniformly this would have proved the theorem. So we claim this, that this is uniformly integrable. Okay. So for that, what is known is that because f is increasing and f is also absolutely continuous. So we use so we have f is increasing and this is the basic assumption that we have. Okay. So we use the absolute continuity. So let epsilon positive, epsilon be positive, be positive number. We must show that there exists delta positive such that for each measurable AB integral is less than epsilon whenever measure of E delta. Now delta independent of H equal to 1. So generally the particular delta would in general depend on the particular function difference f divided difference or the divided difference functions if fh. But what we want to prove that this is independent of the choice of h. Now we need to make some structural analysis of the set, because we have to connect it with the absolute continuum. Let us work on. Now, a measurable set E is contained in a G delta set G, for which G's measure of G slash E is equal to 0. The difference between G and E is only a set of measure 0. So, what are G delta sets? G delta sets are intersection of a decreasing sequence of open sets. Well, in fact, it is the intersection of open sets. So, we can choose in such a way that it is the intersection of decreasing sequence of open sets. Now, every G delta set is the intersection of a descending sequence of open sets. That's the general structure of G delta sets. Now, the sets, it is a subset of what we are talking about, is a subset of an interval. Okay. Further, every open set is the disjoint union of a countable collection of open intervals. Now this is an important step. Is union of disjoint union of open intervals. Therefore, which implies every open set is the union of an ascending sequence of open sets. Each open set is the union of a finite disjoint I'll put it this way, is the disjoint union of a finite collection of opens. Is the it's better. Disjoint union of a finite set of finite collection of open intervals. Now we have come to a stage where we can make use of what is called the absolute continuity of the given function. So let us do that. So this is the basic preparation that is required to use the absolute continuity of the function. We shall do that. Therefore, by continuity of absolute continuity of so let us work on that. By the continuity of integration, by the continuity of integration, it is sufficient to delta positive such that a disjoint collection of open intervals of AB of AB integral over E difference function f is less than epsilon by 2 if where that's what we want. Okay, so that would give you uniform integrability. Irrespective of what h you have for the entire class of functions for a given epsilon, there exists a delta such that we have managed to bring in the disjoint intervals into the picture by considering what is called approximation through G delta, etc., etc. Okay. So we shall now just do that. Choose delta positive as corresponding to epsilon by 2 in the criterion for absolute tension. That is, what is that? That's equal to whenever this is the condition that we have in our hands. Okay. Now observe that integral u to v for any u and v difference, this is equal to, what is this? Integral u to v f of h yes, and by a change of variable, integral u to v is equal to 1 upon h integral 0 to h gt t. This is just a simple change of variable. As we have done in last lecture, this is very simple. We have two integrals here, one corresponding to Krishna, one corresponding to Krishna. Now you use the change of variable. Here you take x plus h equal to t. Here the same thing, integral u to t. Therefore, if you rework this one, where gt equal to 1, where gt is, this is equal to f of for 0, 1 and a so this is a general, very simple to do this. Now we apply this. Therefore, if is a disjoint collection of open subintervals of AB, we have the following: integral over E this is equal to 1 upon h integral 0 to h gt dt. So you don't confuse with this, so okay. Don't confuse with this one, or if you want, you can put a g delta t, where g tilde t is equal to k equal to 1 to n, because here we have E equal to un. This is a disjoint union. This is equal to You see that this is this we have assumed that f is a monotonically increasing function, therefore this is positive, therefore you don't need the absolute value. Okay, now let us use this. So if less than delta, that is the measure of P. This is the measure of then one we have sigma is a translator minus less than delta, and consequently just T cancels that, which implies GT is less than epsilon, where GT is this, or G tilde T is less than epsilon. What does this mean? Thus, the divided difference function is uniformly integrable since integral over E divided difference is equal to 1 upon H and GT is non-negative. Therefore, you see that this is less than, see mod GT is the same as GT. So, this is less than epsilon by 2. Therefore, this is less than by 2. Epsilon by 2. And that implies the divided difference functions is uniformly integrable, and that's what we wanted. That we had proved two things now, that is the equivalence of two statements, or we have connected the absolute continuity of f with a property of the divided difference function associated with f. And this is a very useful result which we shall make use of in our next theorem, which finally leads to the fundamental theorem of calculus in the context of Lebesgue measurable functions. So we make some remarks now from what we have already done. So what are things we have put? Some remarks that we have are the following. This is of course the end of the for a non-degenerate closed bounded interval maybe we have already proved the what we have is the Lipschitz continuous functions on AB. They are continuous functions, of course, is properly contained in the absolutely continuous functions on AB, which is also properly contained in functions of bounded variation on. These are all proper contained, and here of course you can give an example which lies between these two classes, is that you take fx equal to 2 by 3 for x belonging to 0, 1, and you have f does not belong to, is not Lipschitz continuous on 0, 1, but f is absolutely continuous on the interval 0. So that is that. Now here what we do is can take the Cantor Lebesgue function is of bounded variation on 0. That is phi belongs to, but phi does not belong to, is not an absolutely continuous function on the interval. Therefore, these are not, the equality does not hold. Okay, they are proper containment. Okay, but what you can say is that, you see, both Lipschitz function as well as absolutely continuous function, they are all functions of bounded variation. Therefore, they can be expressed as the difference of two functions of bounded variation, two increasing functions of bounded variation. Therefore, what more you can say? What further you can say is that if f is Lipschitz, then these difference functions are also going to be Lipschitz continuous. If f is absolutely continuous, then it is also going to be the difference functions are also going to be absolutely continuous. So let us just put that for clarity. So any f where g is increasing, h is increasing function, and g, non-decreasing rather, and both g will, comma h therefore if f belongs to then f is equal to g minus h, where g and h are non-decreasing functions of bounded range. But what we get is more. That is, f belongs to Lipschitz AB implies g, comma h belong to further. If f belongs to is absolutely continuous on AB, then g and h are not only functions of bounded variation, increasing functions of or non-decreasing of bounded variation, but are also absolutely continuous on. So this is the beauty of the whole. Okay, you have this containment relation, and this one can be split as the difference of two non-decreasing functions of bounded variation. Consequently, these functions are also can be split into non-decreasing functions of bounded variation. But they are not only functions of bounded variation. If f is in Lipschitz, then both g and h are also Lipschitz. If f is absolutely continuous, then both g and h are also. So they stay within this class. Okay. So what you have is a class like this. This is a containment. And they are split up also, stay with them. So f is equal to this split up is there, both g, h, and they belong to the appropriate class. That's a very useful result. Further, you know that linear combination of Lipschitz continuous functions are also Lipschitz continuous. So this forms a linear space. So also this collection also forms a linear space. So also this collection also forms a. So they are linear spaces. So these are all linear spaces. I think we stop here today's lecture. So thank you very much. We will continue with it and now proceed to prove the analog of the fundamental theorem of calculus for Lebesgue integral functions. Thank you very much.